Our second example of an oscillatory reaction is much richer and also much more interesting, and it's a model for the chemical reaction of glycolysis. Glycolysis is a chemical reaction whereby cells break down sugar in the body. And it's a complex chemical reaction, and I'm not going to deal at all with the underlying chemistry of it, but I just want to extract from it its simple dynamical model that describes the behavior of two chemical species that underlie this reaction. Let's write down this model. And so there are two chemical species, X and Y, and their equations of motion are the following. So X dot is equal to minus X plus AY plus X squared Y, and Y dot is equal to B minus AY minus X squared Y. So it turns out that in the body, when this chemical reaction is taking place, the breakdown of sugar is happening not in a monotonic fashion, but can actually go into self-sustained oscillations. We want to try and understand that. And so the simple model was invented to try and describe it. And so let's now treat this simple two-dimensional dynamical system and apply the methods that we've learned to try and analyze its behavior. So the first thing we might look for are the nullines. So setting X dot equals 0, then solving for Y as a function of X, we get the equation for the nullline Y, which is equal to X divided by A plus X squared. Similarly, the nullline Y dot equals 0, we do the same thing, and it's a simple matter to find that Y is equal to B divided by A plus X squared. In fact, these equations are sufficiently simple that we can go even further and find the fixed points, because if we set the two nullines equal to each other, their intersection defines a fixed point. The fixed point is given by X star is equal to B, because we set the right-hand sides equal, then X star has to equal B. And similarly, Y star, now that we know what X star is equal to B over A plus B squared. So we have both the fixed points and the nullines. But now let's analyze the system in the phase plane. So let's plot as a function of X and Y the behavior of the nullines, and they are in turn determined by the values of A and B. So the nullline X dot equals 0 starts off linearly with X and then decays like 1 over X. So here's a representation of that nullline. So this is the nullline X dot equals 0. And the nullline for Y dot equals 0. So at X equals 0, it starts out at B over A. And we see that for large X, it falls off as 1 over X squared. So it falls off faster than X dot nullline. So it's going to intersect at some point. So it looks something like this. So this is a nullline Y dot equals 0. And so there's a fixed point here whose stability we're going to try and determine. Now, if we look at the X dot equals 0 nullline, we can infer what is the behavior just above and just below it. So on the nullline itself, there's no horizontal flow. And one sees that from the equation of motion itself, that if we're just above it, if Y is a little bit bigger, then that's a positive contribution to X dot. So we have the flow, the horizontal flow like this on the X dot equals 0 nullline. And similarly, on the Y dot equals 0 nullline, the same considerations, we find that the flow looks something like this. So now let's use that to infer the flow patterns in each of the little 4 regions defined by the intersection of these two nullines. And here we see why we spent so much time on looking at linear nullines at the start of the discussion, because even if we have nonlinear nullines, locally they look linear, and all of the analysis that we developed for linear nullines goes through for the case of some arbitrary curves for the nullines. In the upper right region, the flow is to the right and down. In this little wedge-shaped region between the two nullines, the flow is down and to the right. Below both nullines, the flow is up and to the left. And finally, in this region, the flow is up and to the right. So this suggests that the flow is going to be some kind of a cycle about the fixed point. What we don't know yet is whether the flow is going to converge into a stable fixed point or whether it's going to end up in some kind of a limit cycle. That's the next thing that I'd like to try and determine. And here we are going to use what we've learned about the Poincare-Bendixson theorem. What we first need to do is to try and define a suitable region of space that we can say that the flow is everywhere inward. And it turns out, if you start looking at the local flows, it almost suggests itself what are the possible regions to define where the flow is everywhere going to be inward. So let's first of all look along the x-axis. So by construction, along the x-axis, the flow is everywhere upward. So it suggests that the bottom of our trapping region should just be the x-axis itself. Similarly, along the y-axis, where x is equal to 0, one sees that the flow is always to the right because x dot is always positive. Let's now define a straight line of height b over a. And let's look at what happens to the vertical flow at this point. So if we look at y dot, where y is equal to b over a, if one looks at the y dot equation, when y is equal to b over a, b minus ay is equal to 0. And as long as x is positive, then the flow is negative. So everywhere along here, the flow is negative. Now, to complete this story, we need to define something else that's going to close this region, because right now it's possible that the flow could leave for y less than b over a and for large x. This is the creative part of this whole story, which is to find another point, another line segment that closes this region where the flow is always inward. And so let's look here at the point b over a. And let's look at a 45-degree line, and you'll see why I chose this in a moment. So this is a 45-degree line that goes to the null line x dot equals 0, and then we close it off this way. So let's now focus attention on this 45-degree line and ask, what is the flow along this 45-degree line? So first of all, this 45-degree line is given by x plus y equals a constant. And what we're interested in is x plus y dot. If we're on this line, x plus y equals a constant, does x plus y increase or does it decrease? And so if we look at the original equations of motion, if we look at x plus y dot, miraculously almost all the terms cancel, and we're left with b minus x. So if x is larger than b, and that's why I chose this upper right point in this trapezoidal trapping region to be at x equals b, and then the rest of the points are larger than b, then we are guaranteed that along that 45-degree line, x plus y dot is negative, and so the flow is inward. And finally, along this part of the trajectory below the x dot equals 0 null line, the flow is again inward. So this region is a trapping region, because if we start anywhere inside of this region, we stay inside of that region. This defines the trapping region, and so we are guaranteed that all flows stay inside of this trapping region. So to figure out whether or not we have a limit cycle, now we have to look at the stability of this fixed point at the intersection of the two null lines.